All right, we just talked about parameterization independence, right? But there's one more independence was that. What was that? For the vector field of line integral, the path independence, right? Path independence of a vector field. So what kind of vector field have a path independence? Yeah, conservative vector field. Mathematically, that was just a gradient vector field, right? So path independence means if you have C1 that goes like this, that's our C1, right? If you go a different way like this, C2, and if you integrate the same vector field, you end up with the same number, the word calculation, if it is conservative or gradient vector field. All right? Makes sense? What was the name of the theorem for this one? Fundamental theorem of line integral. That gives you the FP minus FA, right? It is only depending on this point and that point, not happen what between because the value is actually calculated like this, right? So it's all about A and B. Doesn't care about this formula. Doesn't care about what's happening in between. That's why it's the same, right? And that was the fundamental theorem of line integral. How did we prove it? You take no, it's not Green's theorem. It was more fundamental than that. So we actually take that FB minus FA, right? That's a quantity asserted by the fundamental theorem. Then you put it inside the integral. How do you do that? By differentiating, right? If you differentiate multivariable integral with one parameter, you get the gradient vector inside, right? That's how we proved it. Put an innocent thing and put it inside the integral by differentiating it, going higher dimensional. That's how it's proved. All right? Let's seek path independence of a surface integral. Okay? Not path independence, so I made up this word, surface independence. They don't use this word, but I thought, well, that's probably a perfect word for to use it. Surface independence of a vector field. So maybe there is vector field out there, it's a weird vector field, such that if you go through one surface and go through another surface, their flux is the same. Right? But it wasn't just random two curves. They share boundaries, right? Starts in the same and ends at the same. So what could be the analog of that? Two surfaces sharing the same boundary. Okay? So here is the one idea. Here, suppose you have a loop. Maybe I have a picture for that. Yes, I do have a picture. So here is flat surface down there, right? That's one surface. Make sense? That's S1. And next surface is slightly different. Next surface is a bulge up like this. The flux calculation of this one and that one turns out to be the same. But what seems to be the common for these two? The blue baseline, right? This we call the boundary of the surface. What was the boundary of this curve, this beginning part and end part? That 2 points are called the boundary. If they share the boundary, it doesn't change. That's the phenomenon up there. Now, if they share the edges, the boundary of the surface, like that, and they might not change. If you just throw in a random vector field there, the vector flux of S1 over S1, flux across S2, it's different. All right? But to me, it's a lot easier to understand what kind of vector field actually have this one in common. Can somebody describe? Oh, there it is. There's the answer. I already wrote it there. If it is really a fluid density vector field, the number of things that pass through this surface, right? And then you can see they enter inside the chamber, right? Then how they're going to escape or turn it in. Number of things inside that doesn't change. So how many things are going across this surface? How many things going across that elliptic parabola surface must be the same. If they're different, this inside becoming losing masses or accumulating mass, that doesn't happen with the fluid passing through. It's constant amount in there. So it's easy to understand what kind of vector field it does it, right? So this mathematical characterization is in question. Fair enough? So you can see there is this weird vector field exists, and it was weird property, but in terms of number of particles is actually easier to understand, right? Okay. All right, let's take a look at the fundamental example, which was Green's theorem here. Right, here's Green's theorem again, and it was formulated slightly different so that you enter three-dimensional space. If you think about Green's theorem, it is all about x and y, right? There's no z in the Green's theorem, really. So line integral in xy plane is formulated as a double integral in xy plane. So here's a line integral of phi. Phi can be anything. It doesn't have to be gradient or anything. Is anything. Is described as a double integral over d. Correct? Yeah. So let's see the second line. That's the same thing, but all of a sudden I throw in the vector k dot k. But probably don't know why I'm doing that, but you can easily verify that these two things are equal because k dot k is 1, right? So 1 times 1, it is equal. Correct? So we can look at this. If you group it different, this is a curl vector, right? Sort of vector field in three-dimensional space because I introduced k here. So this one is always rushing upward, right? Or downward. It's a vertical vector. Everywhere is moving vertical upward. Dotted with k, we can look at this k as what of d? Normal vector of d, that's right. Then we enter surface integral. So Green's theorem is just a double integral. By doing that, we interpreted the surface integral. Here is a vector field in three-dimensional space, always in the direction of upward or downward. And then here's a normal vector for our surface d, which is interpreted as a surface sitting inside three-dimensional space, not just xy space. Then this is a surface integral, right? Therefore, I can write it like this. Surface integral of d of this one with whatever parameterization you have, parameterization-free notation. So if I recognize this d as a curved surface, which is actually flat in the space, and then we have a statement like this. Okay? So that gives us an idea of how to generalize that line integral and kind of formulate the flux property. So here's the thing, that this indicates that even though S is not too free, this surface integral is depending only on the line integral, what is on the boundary. That is indication, right? If it's really happening with S1 and S2, replace it in here. If we can have a theorem like that having a common boundary, and that's a proof that it doesn't matter what happened in between. All that matters is what happened in the boundary. So as long as they share the boundary, the flux is the same, no matter what happened in between. So that's their idea, to generalize this phenomena to the higher. So that worked with a curl of this limited definition. So how can we, if this here at the beginning, this phi is xy vector, right? So what would be the version of curl of phi for phi being xyz vector in the three-dimensional vector? So this curl is only for xy two-dimensional vector. So here's the idea. Here we wrote down the curl formula in this way, and what was the very motivation, if you think about it, of the curl, is this gradient vector. If you write down gradient vector like this, and if you multiply these two, so-called multiplication is operator multiply this one, then it's really operator. As you multiply, you get fxy, right? fyx, because it's the operator in the subscript notation. We write it to the right side. What about this one? fxy, right? Differentiated y. So that's equal to like this. That's awkward notation in different order. Remember that part? Yeah. This one was with respect to that. And these two things are supposed to be equal to the same, right? Okay, so they can describe it like this. So if you started with gradient vector field, just like this, if you curl it like this one, and what happened to the curl? It becomes 0 because these two are equal to each other. So curl being 0 tells you if the C is a closed curve, curl being 0, that means this is 0. So we already know the line integral of a closed curve over the gradient vector field is 0, right? But this is a slightly different point of view, higher dimensional point of view. If this, because the curl is 0 here, therefore this is right side is easy. Double integral of 0 is of course 0. Okay? So if this is not a gradient vector, if you just put a random x and y component, you consider that that's just curl, not necessarily 0 this time, right? So they decided to extend this one. Maybe that's going to work. And here is their motivation. Why don't we do that with all three variables? Let's try that. If you have scalar function of 3 variable, then we have 3 partials available, right? Correct? Let's calculate. What are we calculating here? Cross product of these two. It's weird because this is not a vector, it's an operator, right? But let's do that cross product thing and it captures the right thing. So let's try the first component. It's I, right? So this removed, you do determinant of remaining 2, right? So what do you see? The first subscript in correct order. What are the 2 letters down there? ZY. That's right. It goes to the right side. What about the negative here? FYZ. Ha! Of course that's 0 again. You can see that locally that's the same thing going on with the different letters in there. Let's do the next one here. What is a? You have to do this one first because it's negative. Remember the cross product x negative. So this is FZX, correct? Minus. How about this one? FXZ. That's J and that's 0, right? They're the same thing. And plus the last one. FYX minus FXY. That was the Green's theorem thing. That pick up K in there. That's a 0 too. So if you take the gradient vector field, and if you consider this type of thing as similar to the curl that we did for XY plane, and you still get a 0 there, right? So there's a good indication that our effort to generalize this phenomenon to 3-dimensional space, maybe it's going to work. So this is your 4th exercise. Go and write this one down in this fashion. Exercise number 4. Compute. The second is written over there. Cross product in quote. Why is it in quote? Yeah, it's not really vector. It is just arithmetic resembles this cross product. And it's interesting that we can just isolate operator like that and treat it as if it is a number multiplied to things. Alright, was it okay? So we'll take find this right RZQX and this one first PZRX, and there is our Green's theorem thing appeared at the very end, QX minus PY. Make sense? Okay. So what is the name of this vector? Anybody remember the name of this vector? Curl. This is the curl of phi if phi has XYZ in it, right? What was the curl of XY? That was just this guy. If you just have XY in it, then if it has only XY in it, what would be the derivative with respect to Z? They're all 0, and there's no Z in it, and R is not there, and things like that. So this generalizes. Make sense? Okay. So, and they try. Okay, that has this phenomena captured in there. So the bold conjecture is that if I have 3-dimensional vector field, this is a line integral around it. If I just stick in the curl in there, is this going to be the same, right? The answer is yes. And that was called Green's theorem, right? What about the next one is called? That's the Stokes theorem. It's I think I summarized it, and let me just summarize it here and also explain that one more item down there. This is what we just did. Neatly summarized there, and there it is. Seems just like the same as the Green's theorem. Looks almost the same. Here is line integral. What's the difference? Here is the difference, right? It has x, y, z in it. That's the difference from Green's theorem and Stokes theorem. And then you go enter not double integral, but what is the name of this one? Surface integral, right? Including the curved surface. And what are we integrating in there? Curl, which is defined like in this fashion in here. Then it turns out to be equal. That's the key thing. It is equal, just like the Green's theorem. Remember, little magic that Green's theorem pulled out. You know, we could do with that theorem. It's going to do the same thing. So this is a parameterization version. All right? Make sense? Okay. So we're going one integral and differentiating, going inside one more integral, things like that. So let's look at this one. C is usually this oriented curve, right? How about S? Is oriented surface. So let's look at a very simple example. Here's a circle in the xy plane. Maybe it's oriented like this. And here's an interior region, right? And S is its own orientation, either facing upward and downward. So what do we mean by same orientation, right? If you have to use left hand or right hand, which one are you going to use? Right hand, right? It's a right hand rule. Take your hand and curl around it. Where's your thumb pointing up? That's the correct direction, right? If these two match, these two things are the same. If they're opposite, not too bad. You just have to flip the sign. Make sense? That's what I mean by that. All right. Who can explain this item down there? Why is this true? If you start with a gradient vector field, if you curl it, right, we just calculated here. This is a gradient vector field, right? We did curl it. We just noticed that everything is 0, right? Therefore, that's the statement is written like this. Yeah, the del operator I didn't really explain. This is a curl thing, but because of this first row occupies with a partial, which is what we do when you calculate the gradient vector field of a scalar function. So they decided to give a name of it as if it is a vector. Operator x and operator derivative y, this is as if it is a vector, and call this delta x cross product with a phi. It's a fun notation, but it makes sense, right? Here is the operator vector, and this is actual vector. You cross product like this, as end quote. And then it is what it is, right? That's a curl vector. So that's my preferred notation, but physicists in electromagnetic field, you see this notation all the time. But that's what the curl is, right? Okay. All right. I think I wanted to explain this phenomenon now with a picture. So this is S, right? Could be any surface. And this is the boundary of it, and they're always equal to each other. Look at here. This is one surface with this boundary, and that's the surface in between. If I keep the boundary and change the surface like this, the flux, number of particles passing through this one and that one must be the same. Why is the same? Not because it's a flux, not because it's a fluid density vector, because of what theorem? Stokes theorem says as long as they have a common boundary, right? The surface is different. The common boundary, they're supposed to be equal to this quantity that only uses the boundary. Therefore, this thing have one boundary, line integral. This thing has another boundary, the same boundary, line integral. Doesn't matter what happened in between, they must be the same. That's the Stokes theorem, right? So that coincides with the property of the fluid density vector. Yes, sir. No, boundary is this one. I don't know what you mean. Boundary. Well, probably it's going to be given and to me, but when someone describes a surface, of course you can use that information to get that boundary out of it. For example, this one, I can create this one with the elliptic paraboloid intersected with a circular cylinder. That's how I created this one. And we used that before. This is elliptic paraboloid with x, y, and the ratio different. And circular thing cut out, it creates this pretzel, what is a Pringle, that shape. And then keeping that the same. The boundary is not projection. I see what you're saying. How to actually get a handle on the boundary. That would be the one idea. But boundary is just blue curve, right? That's the boundary, right? Yeah. So that's the same thing. All right. 2 more pictures, I'll let you go. This is another one. Do you see the boundary down there? Right? This, if it is a curl of phi, that flux going through this one and flux going through that one, they're all the same. It doesn't matter what the surface is as long as you have the same boundary and the flux is the same. For what kind of vector field? Not conservative. Not fluid density. And mathematical characterization of that is curl of another vector field. That's the answer. If the vector field you have is a curl of another vector field, then it has this incredible property. The flux does not depend on, only depends on the boundary. So there's a fluid vector field going through, and first year calculus physics student, oh, that makes sense, and then you have amazing description of that fluid density field. What is it? That's actually curl of another vector field, and that's fancy. I'll see you tomorrow.